A very good afternoon, everyone. I am Agrani Sharma, along with my co-authors Anshika Chaurasia and Deepu Kumar. And we worked on Neuro-Sync, a real-time framework for effective state decoding and spectral telemetry using machine learning. Basically, emotions are still complex psychological states, which is inseparable part of human life, right? And that involves three kind of components: physiological response, subjective experience, and behavioral expression. Can you change the slide, please? Hello, am I audible?
Yes, we can hear you.
Okay, so physiological responses basically refers to the change in the body, such as brain activity and the heart rate. Basically, the heart palpitations we have, right? This is what EEG and ECG tools measures, right? But the main problem in the current emotion detection method cannot accurately detect the hidden emotions, especially in today's high stress environment. For example, a person may be under a stress, but still appears normal or even smiles. He thinks part of life and he's stronger, but what actually happening, this creates a gap between internal feeling and the external expressions, which directly impacts on the mental health. This, therefore there's a need for a system that directly understand the internal emotion states in a way that is simple, accessible, and efficient, but not complex. To solve this problem, we use EEG, electroencephalography technique, which records the electrical activity of the brain in the form of brain waves. Based on this, we developed Neuro-Sync, a real-time framework for effective state decoding and spectral telegraphy using machine learning, which uses EEG signal to detect and classify human emotions. The brain waves generates different type of waves such as alpha, beta, gamma, which each associated with different mental and emotional states. And we trained our model using Dreamer dataset, which contained EEG recordings along with the emotional labels. Since EEG captures direct brain activity, it provides more reliable insight compared to the traditional methods like facial expressions or speech recognition. One of the main reason why we chosen the data set is it is based on the dry EEG recordings. Mostly commercially available EEG devices, such as emotive headsets like we used in our model, is basically using dry electrodes, making our system more practical and compatible with the real world applications. This Dreamer dataset consists of EEG recording from 14 different participants exposed to 23 emotional stimuli. These recordings are labeled based on emotional dimensions such as valence and arousal. Now, I really want to get into the methodology part with Deepu Kumar.
So, good morning, everyone. I am Deepkumar and I am here to deal with the methodology section, how actually we implemented our whole system and how it works. So first it starts with the data acquisition and pre-processing. So everything starts with data. We utilize Dreamer dataset, which is superior for modern application because it uses 14 channel dry electrode montage, which accurately reflects the signal to noise ratio found in portable BCI hardware. We take raw EEG data, which is actually containing a very large amount of noise. So to overcome this noise, we implemented a fourth order Butterworth bandpass filter, which strictly limited the frequency between the 4 Hz to 45 Hz. Beyond this limit, it eliminates all the data which data beyond this limit. We also implemented the 10x decimation, which reduces computational load without violating the Nyquist-Shannon theorem, ensuring we retain the signal's morphology integrity. Second, it's like feature engineering. The Wells powers spectral distribution. Once the data is clean, we move from time domain to frequency domain. We don't look to the vigilance, we look at the power spectral density using the Wells methods. It basically categorizes all the frequency into four categories. First one is theta, second one is alpha, third one is beta, and the fourth one is gamma. This creates a high dimensional features vector for each of our 14 channels, giving the AI a precise neural fingerprint of the user's brain state. Third one is the AI engines, basically the machine learning model, which we are using. For our classification, we choose a random forest model with 100 decision tree. We intentionally avoid black box like deep learning model because it uses weight electrodes, which is not feasible in the real world. We also implemented the Gini importance to see exactly what brain regions like the frontal lobe are driving the detections. We followed a rigorous 80-20 scientific split across a 2038 lakh data frames. Our model achieved a validated accuracy of exactly 70.78%. To put that in perspective, in a four-class problem where random generously in only 25%. Now, fourth one is implementation, where we implemented the our whole software. So it's decoupled into a three-layered architecture. First one is backend, second is frontend. In the backend, we implemented a Python Flex API that hosts our trained model. In the front end, it is a high-performance dashboard with Tailwind CSS and vanilla JavaScript. The real-world implementation here is our temporal majority logic. Unlike static systems that give our one result per second, our system analyzes the entire session at the same time. We also integrated bioacoustic feedback using the web audio API. The system generates a neural arm that guides a pitch based on the detected valence. Finally, we implemented professionals a medical report generator. That is the one of the key features of our innovation. With one click, the system captures the 2D effective map, the spectral waveframes, and the AI insights into a verified PDF. And we also verified with the human interface itself. Now we move on to the results section. So actually, our system implemented the exactly accuracy of 70.78%, and we also classify it on the basis of different classes like happy, calm, stressed. That all are the classes that we implemented on it, and they are also overall accuracy of around 70.78%. Now we call Ansika to carry on the presentation.
So in this work, we developed an EEG emotion recognition system using the Dreamer dataset. The EEG signals were processed and converted into frequency-based features such as alpha, beta, and theta bands. The model achieved an accuracy of around 70.78%, which indicates that EEG signals can be effectively used for emotion recognition. In addition, the system provides visual outputs such as EEG signal graphs, frequency band analysis, and automated report generation, making the result easier to understand and interpret. The system also includes a live reading feature. By connecting an emotive EEG headset via Bluetooth, it can capture real time brain signals and predict emotions instantly. Overall, the system shows promising results, although there is still scope for improvement in terms of accuracy and scalability. So, move to the future work. In future work, the system can be improved by using larger data sets and advanced techniques like deep learning, which can be further enhanced and accuracy and reliability. It can also be extended into real world applications such as mental health monitoring and affective computing. So, for the references, we refer to the various research papers and IEEE publications related to EEG based emotion recognition, especially the DREAMER dataset paper for methodology and data understanding. Thank you so much. We would happy to take your questions.